We're going to continue these transformer problems. Here's number 2. And this time there's a new twist. It says a transformer has a ratio of primary to secondary turns of 6.67 times 10 to the minus fourth. I guess a secondary, another twist is that this time they give us the voltage in the secondary and the current in the secondary, and so they want to know the primary voltage, the primary current, the primary power, and whether it's step up or step down. So let's deal with this ratio thing first. So the ratio of primary to secondary turns. Anytime it says this, you'll notice in the next problem it does this as well. Whatever comes first, the number of turns in the primary to the number of turns in the secondary, which is the second thing, you set that up as a ratio in the following way. Alright, so let's take a quick look at it. So this is what you do. So because the number of turns in the primary was first, you put that in the numerator, and the number of turns in the secondary was second. So the ratio of primary turns to secondary turns, the word to is division, right? So the number of turns in the primary to the number of turns in the secondary is equals 6.67 times 10 to the minus fourth. They also gave us the voltage in the secondary and the voltage in the so the voltage in the secondary and the current in the secondary. So you treat it just like when we were solving for the secondary voltage and the secondary current. Well, the first thing that we can do is, of course, answer part C, which is what's the power in the primary, which is, of course, equal to the power in the secondary, which, since we know the voltage in the secondary and the current in the secondary, we just multiply those two together. Okay, so that's 0.26 amps. It's not coming out. Times 5,300 volts. Okay, that's 5. All right, so let's quickly see what that is. So the 0.26 times 5,300, I get 1,378. All right, so 1,378 watts. All right, so that's the power in the primary, which is also the power in the secondary. So remember, we can always answer that question first because we're given two numbers that'll allow us to do that. All right, so the next thing is we're going to have to get the voltage in the primary. Okay, so that's question A. And so if we rearrange the equation, just the same as when we solve for the voltage in the secondary, we just bring the n sub p over, right? And so the n sub p is going to be divided by n sub s, right? Because that was in the denominator already, times the voltage in the secondary, which we now know, which is given to us. But notice this number of turns in the primary divided by number of turns in the secondary is given to us. That's already there. That was given to us. So you can replace n sub p over n sub s in this equation with 6.6. Here, let's do it. 6.67 times 10 to the minus fourth. So that literally is n sub p over n sub s, and remember v sub s was what, 5,300, so multiply by 5,300 volts, and that'll give us our voltage in the primary. And notice this number is far, far less than 1, so it's only going to be a small fraction of 5,000. So we can already, well, let's actually solve for it, and we'll see what it is. Okay, so 6.67 times 10 to the minus fourth times 5,300. I get 3.5 roughly. So 3.5 is our voltage. 3.5 is our voltage in the primary. And so we can, this was part A, so we just answered part A. We can actually now answer part B, but before we do that, let's actually answer part D, which is it a step up or step down transformer? So part D, and so let's take a look at it. The voltage in the primary is 3.5, right? But the voltage in the secondary was 5,300. So we know that the voltage in the secondary is far greater than the voltage in the primary. It doesn't have to be far greater, it just has to be greater. And so let's see. And sometimes people ask me, well, what if they're equal? Well, if they're equal, you really have, the transformer hasn't done anything. So the purpose of the transformer is to really change the voltage, either from a high voltage to a low voltage, which is a step down, or in this case, from a low voltage to a high voltage. And so that's a step, where's my T? Up. So that's a step up transformer. So we've answered part D. Let's finish this one, and we'll answer part B, which is what's the current, not in the secondary, we want to know the current in the primary. So that's going to be the current in the secondary times the voltage in the secondary divided by the voltage in the primary, right? So just go back to our original equation and solve for I sub P. Now we have all that information, right? So we have 0.26 times 5,300, which we already did basically, 0.26 times amps times 5,300 volts divided by what was it, 3.5, right? 3.5, the voltage in the primary that we just solved for. Notice the volts cancel, and that'll give us our current in the primary. Okay, so let's take a look at that. 0.26 times 5,300 divided by answer. I get 389.8. 389.8, or around 390, right? So I'll just put 390 amps. It's close enough. And there's another one of our problems. All right, and here's the third and final example. It says, and this is of course another twist. A transformer has a ratio of primary to secondary turns of 13,000. So right away, let's just look at how to write that. So whatever comes first goes in the numerator, whatever comes next. So the number of turns in the primary to the number of turns in the secondary is 13,000. Now the twist is, let me go back to the problem. It says if the primary has 8,450,000 turns, how many turns does the secondary have? So this is just another twist to this kind of question, and then the rest of it is exactly like we just did. So let's take a look at that. So we have this, we have N sub P over N sub S is equal to 13,000, but we know N sub P is equal to 8,340,000. Let's make sure I got that right. 8 million. Oh, no, I got that wrong. 8,450,000. Sorry. Here, let's just wipe that out. Sorry about that. So let's see. It was 8,450,000 turns. Okay, so forget that first thing that I put. Sorry about that. At any rate, we want to know the number of turns in the secondary. So how do we do that? How do we solve for the number of turns in the secondary? We know the number of turns in the primary. Let me rewrite that just to make sure it's clear. Number of turns in the primary is 8,450,000. I think I was looking at another example. Sorry about that. All right, so how do we solve for it? Well, we just use this equation, right? This equation we can solve for N sub S. Right, and so let's do that very quickly. So I'm just going to multiply both sides by N sub S, N sub S, N sub S. Right, the N sub S's cancel on that side, and so now I have N sub P equals 13,000 times n sub s. To solve for n sub s, I'm going to divide both sides by 13,000. So n sub s is equal to n sub p divided by 13,000. So that, and now we can just put in the numbers, right? So because we already know what n sub p is. So to solve this, let me go down one more row. So this is going to be, I'll put the number in, 8,450,000. Oh, that didn't come out very nicely. 000 over 13,000. All right. And of course these three zeros cancel these three zeros. And let's see what it is. All right. So I get 650. 650. So that's the number of turns in the secondary. It's 650. All right, so we've answered that. Let's see. Let's finish it up. So they gave us that to continue this problem, the voltage in the secondary is 350. The current in the secondary is 45. So I've just just put them right here, just to have them. And so remember, the number of turns in the secondary to the number of turns in the primary, the original thing that was given to us is 13,000. So we could actually solve for the voltage in the secondary. So this is going to be 13,000. Remember, that's what this part is, times 350 volts. So that'll give us the part A, which is this is part A. Of course, we could have done part D, sorry, not part D, part C first by just multiplying, because the power in the primary equals power in the secondary, and these two numbers here give us the power in the secondary. So it's just 45 times 350. I should have done this first. 45 amps times 350 volts, and whatever that turns out to be. Let me do that real quick. Let's see. So 45 times 350. I get 15,750. 15,750. That's 5. And of course that's watts. So that actually answers part C. Let's see, so 13,000 times 350 will give us the voltage in the primary. So notice this is a huge amount of voltage. Let's see, 1, 2, 3, 1, 2. So it's going to be 4,550,000, 550. That's a 5, and then 000 volts. And so we can actually answer part D now. It goes from 4,550,000 to 350 volts. So I think that's pretty clear that in part D the voltage in the secondary is less than the voltage in the primary, far less in fact. This is of course a step. It's supposed to be an S. It's supposed to be an E. Down, right? So that's a step down transformer. And then the final one, part B, is to get that final current. So this is the current in the primary, and of course that's going to be the current in the secondary times the voltage in the secondary, which we know both of those, and now we know the voltage in the primary. All right, and so that's going to be, let's see, let me calculate it real quick. I get a current of only 0.00 3.5 roughly. 3.5 amps. That's supposed to be a 5. All right.